Hi everyone, I am Nabil and I'm currently working as a research and development engineer affiliated to Green Tech Institute at Mohammed VI Polytechnic University, Benguir, Morocco. Today I will be presenting our latest research on PMSM temperature prediction using MLP-based model enhanced by feature dimensionality reduction techniques. Showing on the screen is the overview of my presentation. I will start with a brief introduction to the context and the motivation of our study on PMSM temperature prediction. Then I will move on to the method and materials, where I will detail the dataset used, the pre-processing steps, and the MLP-based model setup along with the dimensionality reduction techniques. Following that, I will present the key results and analysis to highlight the model's performance. The discussion will cover insights, trade-offs observed, and implications. Finally, I will conclude with the main findings and suggest direction for future work. So let's begin. This study builds up on our previous research titled Predicting the Temperature of PMSM, Comparative Study of Artificial Neural Network Algorithms, where we evaluated the performance of several INN architectures for PMSM temperature forecasting. In that work, the MLP model emerged as the most effective in terms of predictive accuracy. The current paper represents a continuation of that effort, focusing on refining the MLP-based model by integrating feature dimensionality reduction techniques to enhance performance and reduce computational complexity. The Permanent Magnet Synchronous Machine, PMSM, drive is one of best choices for a full range of motion control applications. For example, the PMSM is widely used in robotics, machine tools, actuators, and it is being considered in high-power applications such as industrial drives and vehicular propulsions. It is also used for residential commercial applications. The PMSM is known for having low torque ripple, superior dynamic performance, high efficiency, and high power density. PMSMs face a range of problems like voltage defects, stator and rotor problems, voltage overheating, etc., which require advanced monitoring and control methods, especially for the temperature. Predicting thermal behavior of PMSM is very difficult due to its complexity, which is characterized by nonlinear relationships between mechanical and electrical parameters. Moreover, temperature affects significantly the efficiency and stability of PMSMs. It mainly causes overheating, one of the most frequent and harmful reasons taking place because of the pressure caused by the mechanical parts of the engine, core iron and copper in stator winding. Copper losses directly influence heating in the stator windings, leading to degradation of engine combustions, the most heat-generating component in it, after which comes an overall system breakdown. Due to this, the engine requires close monitoring and control so that its operation fails within the permissible limit of temperature. The dataset used in this research consists of sensor data from a prototype PMSM of a German original equipment manufacturer, OEM. The data was collected during a test experiment conducted at the LIA department of the University of Paderborn. This recording evaluated the performance of the motor in their different operating conditions with a sampling frequency of 2 Hz. Each measurement session has a duration of 1 to 6 hours and can be identified by the profile ID columns. The prediction of PMSM temperature using an MLP model integrated with feature dimensionality reduction (FDR) follows a structured approach to enhance accuracy and efficiency. The process begins with data pre-processing, including normalization to standardize feature scales, cleaning to remove inconsistencies, and imputation to handle missing values. Two FDR methods, which are correlation analysis and PCA, which is principal component analysis are applied to optimize feature selection. Correlation analysis eliminates highly correlated features with a threshold of 0.9, while PCA extracts K components capturing maximum variance, producing reduced and transformed datasets. Each dataset's configuration original, then correlation analysis reduced, and principal component analysis transformed, is split into training and testing sets for MLP modeling. Here is the definition of each feature dimensionality reduction techniques, which are correlation analysis and the PCE, which is principal component analysis. The correlation matrix derived from the original normalized dataset shown in the figure indicates the presence of several features that are strongly correlated, which may suggest redundancy within the dataset. In particular, the features stator winding and stator tooth demonstrate an exceptionally high correlation coefficient of 0.99, implying that they provide nearly the same information. Additionally, stator yoke shows a strong correlation with both stator winding and stator tooth, further highlighting the issue of feature redundancy. Furthermore, the variables IQ and torque exhibit an almost perfect correlation of 0.9, suggesting that it may be feasible to eliminate one of these features without a significant impact on the overall information retained. After applying correlation analysis with a 0.9 threshold, highly correlated features from the original dataset have been removed. Stator yoke and stator tooth, which were redundant, are no longer present. The remaining features exhibit lower correlations, reducing multicollinearity and preserving relevant information. This selection improves computational efficiency while maintaining predictive abilities. So after applying PCA, principal component analysis, the dataset is transformed into 6 principal components that capture approximately 100% of the cumulative explained variance. Unlike the correlation matrix after correlation analysis, where some correlations remain, this PCI transformed matrix shows completely uncorrelated component diagonal matrix. This ensures dimensionality reduction while preserving all essential variance, improving model efficiency, and eliminating redundancy. Accurate prediction of temperature in permanent magnet synchronous motors have always been essential for monitoring performance and enabling predictive maintenance in the industrial sector. This study examines the efficiency of a set of artificial neural networks models, namely multi-layer perceptron MLP, long short-term memory LSTM, recurrent neural network RNN, and convolutional neural network CNN. In predicting the permanent magnet temperature, a comparative evaluation study is conducted using commonly performance indicators, including RMSE, MEE, and coefficient of determination to assess the predictive accuracy of each model. The intent is to identify the most favorable model that balances high accuracy with low computational costs. As illustrated in Figure 6, the performance of the 3 MLP models is evaluated based on the predefined indicators and execution time for each combination. This analysis offers a comprehensive representation of their predictive capabilities, leveraging the FDR techniques. The bar chart compares the performance of 3 FDR techniques applied to an MLP model using the predefined performance indicators. As the principal component analysis transformed dataset achieves the best results with the lowest MEA and MSA, indicating better predictive accuracy while maintaining a high coefficient of determination. The original feature dataset performs slightly worse with a higher MEA and MSA, but it still retains a strong coefficient of determination score with 0.99. The correlation analysis reduced datasets demonstrates the weakest performance despite having a relatively high coefficient of determination. Overall, the PCA transformed dataset is the most effective choice for improving model accuracy and reducing errors. The analysis of execution time reveals that the PCA transformed model is the most computationally efficient with a runtime of 88 seconds. This is in comparison to the 116 seconds required by the correlation analysis reduced model and the 123 seconds of the original feature model. Although the principal component analysis improves execution time, it has the potential to cause information loss, which can affect the interpretability. Correlation analysis reduction slightly reduces computational costs but does not significantly enhance accuracy. The study is limited to MLP models, which restricts generalizability to other architectures. Future work should explore alternative feature selection methods and broader model applications. So coming to the conclusion, the principal component analysis transformed dataset is the most effective choice for improving model accuracy and reducing execution time. The correlation analysis reduction balanced well between accuracy and computational efficiency. Using all original features gave a good accuracy but required the most processing time. Here is a list of references used in this research paper. Thank you for your attention.